There's a rock on Mars right now, sealed inside a metal tube about the size of a stick of chalk. It was drilled out of a stone the science team named Cheyava Falls in the summer of 2024. The rock carries small dark markings. The people who found them call them poppy seeds and leopard spots. On Earth, patterns like those would be a textbook signature of microbial life. Last September, after a year of careful review, NASA's official position landed on one careful phrase. The sample contains a potential biosignature. They're extraordinarily careful with that word. Potential. Nobody is saying life. Not yet, but the tube is still there, sitting on the surface of a world that died something like 3.5 billion years ago. And the earliest we might bring it home is the late 2030s. Tonight, we're going to talk about that rock. But not only that rock, because Mars isn't the only dead world. It may not even be a rare one. What we're really doing is sitting with a question that doesn't get asked often, mostly because it makes people uneasy. The universe, as far as we can tell, holds a confirmed inventory of just over 6,000 worlds beyond our solar system, and a credible estimate of hundreds of billions more in our galaxy alone. The natural assumption is that some fraction of those should be alive. Someone should be home. But the more we learn about what it actually takes to keep a world habitable, the more the real story looks like it isn't about life starting. It's about life lasting. By the end of tonight, you'll see the night sky a little differently. Not as a place that's empty, but as a place that might be very full of something quieter than we expected. Something that already happened. Something that ended. Here's where most people get the universe wrong. When they think about whether anyone is out there, they picture two doors. Door 1. The cosmos is teeming with company, and we just haven't run into them yet. Door 2. The cosmos is empty, and we're alone. Those are the two answers people argue about. There's a third door. That's the one we're walking through tonight. It's the possibility that the universe isn't empty at all, that it's full of worlds where the conditions for life arrived and then left. World where life may have started and then stopped. Worlds with the light still on and nobody home. If you're finding yourself sitting with that image of the sealed tube on Mars, take a moment to like the video or subscribe. It genuinely helps this channel reach more people who want to think about this stuff at 3 in the morning instead of being yelled at about it. That's it. Now back to it. The number to sit with first is 6,087. That's the count of confirmed worlds outside our solar system as of January 2026. In the NASA Exoplanet Archive, NASA crossed the 6,000 mark in September 2025. For scale, there are about 195 sovereign countries on Earth. We have more confirmed worlds beyond our solar system than countries here, by a factor of 30, and those are just the ones we detected. There are roughly 200 billion stars in the Milky Way. Based on Kepler and test data, nearly every star has at least one planet. So the arithmetic lands on hundreds of billions of planets in this galaxy alone. Of those, the latest estimates put the number in the habitable zone, the region where liquid water could exist on a surface, in the tens of billions. That's a lot of worlds. So why is it so quiet? The first thing to understand is that habitable zone is a misleading term. It only means liquid water could exist there in principle. It doesn't mean water is there, or ever was. It doesn't mean the planet has an atmosphere that can hold water, or that the surface temperature is in the right range. It just means the orbit sits at roughly the right distance from the star. So when you hear there might be tens of billions of habitable zone planets, what's actually being said is that there are tens of billions of orbital slots where conditions aren't ruled out. They could still be ruled out by 1,000 other things. And very often they are. Most of the 6,000 confirmed exoplanets are nothing like Earth. The first we found were hot Jupiters, gas giants so close to their stars their atmospheres glow, the easiest to detect. Then came super-Earths, rocky worlds bigger than ours, often in orbit so tight a year there lasts a few Earth days. Then tidally locked planets, one side facing the star forever, the other facing away, a permanent day baked into rock, a permanent night, so cold the air can fall as snow. Then scorched orbits, stripped atmospheres, surface gravity too high for a human heart to keep beating. The planets that resemble Earth in any meaningful way are rare. Of 6,000 confirmed worlds, the number that are roughly Earth-size, in roughly the right orbit, around a roughly stable star, is in the low dozens. So, part of the silence is just that most of these worlds were never going to talk to us. They don't have the chemistry, the temperature, the air, the time. They're stones in space. But that's only part of it. The truly strange thing isn't the worlds that never could have been alive. It's the ones that maybe could have been. The Earth-like candidates are out there in real numbers, even by conservative estimates. And from those, we have no signal. No radio call, no optical flash, no chemical fingerprint we can identify as life. Nothing. That's the silence that's hard to explain. The silence of the worlds that should, by any decent statistical argument, have something on them. There's an image I keep coming back to. The universe, at least the part we can see, isn't quiet because nobody ever existed in it. It's quiet the way an old library is quiet. You walk in at night and the lights are off, but the building is still there. The shelves, the books, every spine has a real author behind it. Real ink, real pages. The library wasn't built empty. Somebody filled it, but it's been a long time. The writers are gone. The readers are gone. The lamps overhead burned out one by one. The building has gone quiet. The books are still there. The voices aren't. When Kepler finds a planet, what astronomers actually see is a star that dims a little every few days or weeks in a regular pattern. The dim is a planet crossing in front of the star, blocking a fraction of its light. That's it. We never see the planet directly. We see a slight repeating shadow, and from it we work out the planet's size, its distance from its star, the length of its year. We don't see what's there. We see that something is there. Then we go to the next star. That's most of exoplanet science. You stand outside the library. From the shadows on the wall, you can tell the building has shelves and aisles and corners. You can guess at the number of books, their size, but you can't go in. And you mostly can't tell from the outside whether anyone ever read them. The other thing to understand about the silence is timing. Even if every Earth-like world developed intelligent life, the odds of any two civilizations existing at the same moment, in a galaxy more than 10 billion years old, are slim. Human radio has existed for about 100 years. Recognizable civilization, around 10,000. Anatomically modern humans, around 300,000. Earth has been habitable for about 4 billion years. Compress all of Earth's habitable history into a single calendar year. An entire span of human existence shows up in the last 90 seconds before midnight on December 31st. Modern science fits in the last second. Now, picture a galaxy where every habitable world has its own version of that calendar, starting and ending at different times. Most of it quiet and ordinary, with only a few loud seconds in each year. The chance of two calendars overlapping in those few loud seconds is small. Most of the time, you'd reach in at random and pick a world that hadn't started its civilization yet, or had already finished it, or never had one. Silence isn't proof of empty. It's proof of timing. Astronomers have a half-joking phrase for this: the Great Quiet, not the Great Filter, which is a specific argument about what stops civilizations from growing. The Great Quiet is just the observation, the listening. The receiver is on, and the signal level is essentially zero, and has been for as long as we've been able to check. Some of that quiet might be that nobody is out there. Some of it is almost certainly that somebody was, and isn't anymore. The library is real. The shelves are full. The lights are off. Whether anyone is still inside is a question we don't yet have a tool sharp enough to answer. What we have is the shape of the building, in a sense, growing every year, of how many rooms it contains. If you want to know what one of those quiet rooms looks like up close, we don't have to travel far. It's the planet next door. Mars is the easiest dead world to talk about because we can see it. Step outside on the right night, find the small, steady reddish light, and there it is, the fourth planet from the Sun, the neighbor you don't have to imagine. For most of human history, Mars was a wandering light and a name for a god of war. It became a place in the late 1800s, when telescopes got good enough to show polar caps that grew and shrank with the seasons, and dark patches some astronomers took for vegetation. The Italian astronomer Schiaparelli reported straight lines across the surface, which the American Percival Lowell convinced himself were canals dug by a dying civilization to move the last of their water from the poles to the equator. None of it was true. The lines were the eye trying to make sense of fuzzy images. The dark patches were dust and stone. There were no canals. But the idea of Mars as a dying world turned out closer to right than anyone realized. The Mars we have today is, by any reasonable definition, dead. The surface temperature averages about minus 63 degrees Celsius, roughly the coldest temperature ever recorded in Antarctica. Except on Mars, that's the average, not the extreme. The atmosphere is so thin that liquid water on the surface would boil and freeze almost at the same instant. Standing on Mars today, even in a perfect suit, you'd feel the cold soak into your boots within minutes. The sky would be pale butterscotch, not blue. There isn't enough air to scatter light the way ours does. The sun would look smaller and dimmer. The horizon would feel close, because Mars is small and the ground curves away faster. It would feel like a place something used to live in. That feeling, it turns out, is correct. Here's what we know. Mars used to have a magnetic field, a real planet-wide one, generated by a molten core spinning at its center, the way Earth's core spins now. That field was a shield. It deflected the solar wind, the constant stream of charged particles the sun throws off. The shield meant Mars could hold on to its atmosphere. It meant surface water could stay water. It meant a sky thick enough to feel like a sky. Then the shield went down. The current best estimate is that Mars's global magnetic field collapsed roughly 3.9 billion years ago. That date has been pushed and pulled. Recent work, including a high-profile Harvard paper in 2023 and follow-up studies through 2025, suggests the field may have lasted a bit longer than we used to think. But the headline is the same. The core cooled. The dynamos stopped. The shield went away. After that, the atmosphere started to bleed, slowly, over hundreds of millions of years. The solar wind picked at the top of the atmosphere, knocking lighter molecules into space one at a time. If you'd stood on the surface watching, you wouldn't have noticed any change from one century to the next. But the budget was negative. More air was leaving than was being replaced. Eventually, the account ran out. Today, Mars' surface pressure is somewhere between 1 and 14 millibars, depending on altitude and season. Earth's is 1,013 millibars. Mars has less than 1% of our air pressure. To find air that thin on Earth, you go up about 30 kilometers, 3 times higher than a passenger jet flies. That's the air Mars has at ground level. But there was a window, a long one, and inside it, things happened. The Curiosity rover landed in Gale Crater in 2012 and has spent over a decade driving up a mountain in the crater's center, reading the rocks layer by layer. Gale Crater was a lake. The mudstones, the river-worn pebbles, the salt deposits, the clays that only form in standing water, all of it tells a story. Around 3.8 billion years ago, this part of Mars was full of liquid water, a deep lake, fed by rivers that persisted on and off for something like 700 million years, the last clearly habitable conditions winking out around 3.1 billion years ago. 700 million years is hard to hold in your head. Complex life on Earth has only existed for about 600 million years. The Cambrian explosion was about 540 million years ago. Mars' surface habitable window lasted longer than the entire history of complex animal life on Earth so far. And on Earth, in that same era, life had already started. The earliest convincing evidence of microbial life here shows up around 3.5 billion years ago, with debated hints going back maybe 3.8 or 3.9 billion. So the two planets were running the same experiment at the same time. They had liquid water at the same time, atmospheres at the same time. One of them, we know for sure, started growing life. The other had every ingredient to do the same. Then, somewhere around 3 billion years ago, conditions on Mars stopped being friendly, which brings us back to the rock. The Perseverance rover landed in Jezero Crater in February 2021. Jezero, like Gale, used to be a lake. You can see the fossilized river delta in satellite imagery. Ancient water flowing in from the highlands, dropping sediment in fan-shaped layers. Perseverance was sent there specifically to look for biosignatures, and it's been sampling that delta since arrived. In July 2024, it drilled into a rock the team named Cheyava Falls. The drill produced a small cylindrical sample, sealed in a metal tube named Sapphire Canyon. The team noticed something unusual right away. The rock contained small dark nodules distributed through the sediment in patterns that, on Earth, would be unusual. Some look like poppy seeds. Some look like leopard spots. Chemical analysis identified them as concentrations of iron phosphate in a mineral called vivianite, along with iron sulfide in a mineral called gragite. On Earth, that combination is interesting. Vivianite and gragite, together with organic carbon and mudstone, in those kind of patterns, are what certain microbes produce when they do their chemistry. Specifically, when iron-breathing bacteria pull energy out of sediments by moving electrons between iron and sulfur compounds. The patterns Perseverance saw are the kind of textbook we call microbial biosignature. The paper describing the find was published in Nature in September 2025. After a year of careful review, the authors are extremely careful with their language. The phrase they use is potential biosignature. They list the alternatives. The patterns could come from chemistry that isn't biology, from certain volcanic processes, from water rock interactions that don't involve life. They don't claim they found life on Mars. They claim they found something that, on Earth, will be the first thing you point to as evidence of life, and that other explanations remain on the table. The sample is sitting on the surface of Mars right now, in its sealed tube. The Mars Sample Return mission, which will bring it home for analysis no rover can do, is in flux, under budget review and architectural change. The current best estimate for retrieval is the late 2030s, possibly later, which means the most consequential rock sample in the history of our species will sit on the surface of another planet for at least another decade, waiting for us to come get it. In the meantime, all we have is the photograph. There's an old idea that photographs aren't so much images of people as of moments. The person you photograph today keeps aging. The moment on the film doesn't. So you end up holding a small rectangle that's a piece of time, separated from the person it came from. That's what Cheyava Falls is. A piece of time. Maybe a piece of Martian time when something was alive. Maybe a piece when no life was ever present. And the rocks just happen to assemble into patterns that look like life would have made them. We don't know. The image is real. What it shows is still being worked out. If you ever moved into a house someone else used to live in and gone up into the attic, you know the feeling. There's a box up there. It has photos in it. Real photos, real people, real faces and clothes you don't recognize, in rooms you don't recognize. You're holding pictures of people who walked through your hallway and ate in your kitchen generations before you bought the place. They're not your family. They're just people. The fact that they were there, doing ordinary things in the same space you now live in, is hard to absorb the first time you really notice it. Mars is like that attic. You climb up expecting dust, expecting nothing, and instead you find a photo album. The pictures are real. They're of someone you've never met. And the camera that took them stopped working a very long time ago. The rock in the tube is the latest photograph from the attic. There may be others. There almost certainly are. The Mars 2020 mission is one of dozens, robotic and orbital, that have studied this planet for 60 years. We've been knocking on the door for 60 years. Sometimes the door rattles. Sometimes a window opens. Mostly, the house is quiet. The wind blows red dust against the porch. Mars's porch light is still on. We've been ringing the doorbell for 60 years. Mars is the obvious dead world. The one that's harder to think about, because it's our actual twin, is the planet on the other side of us. The one we skip past in school. The one we file under hot rock and stop thinking about. Venus. We don't think about Venus the way we think about Mars. Mars gets the cultural attention. The rover planet. The future colony planet. The magazine cover next to a square-jawed person in a spacesuit. Venus we mostly skip. You learn about it for about a week. It's the runaway greenhouse. The too hot one. The greenhouse gone wrong example. And then you move on. That telling is wrong. Or at least, it's missing the most important part. Venus, on paper, is Earth, almost exactly. Same diameter, roughly. Same mass, same density. It formed at the same time, out of the same protoplanetary disk, from the same mix of materials. It's our sister world, by every standard astronomers use to mean by that term. Show a strange of the basic specs of two planets, one labeled Earth and one labeled Venus, and ask which one supports life. They have no way to tell. And here's the part one thing people should sit with. Venus may have been habitable, with liquid water oceans on the surface, for as long as 2 to 3 billion years. That's not wild speculation. It's a conclusion of climate models from NASA's Goddard Institute for Space Studies. The Way and Del Genio simulations, published in 2016 and refined since, take what we know about Venus's likely early conditions, run a 3D climate model forward, and find that under reasonable assumptions about cloud cover and rotation, Venus could have had a stable, temperate climate with surface oceans for somewhere between 2 and 3 billion years before it tipped into its current state, 2 to 3 billion years. Complex life on Earth has been around for about 600 million years. Venus, on this timeline, had liquid surface oceans for longer than complex multicellular life has existed on Earth. 5 times as long, give or take, there was, on that planet's surface, an environment that by any reasonable definition would have been habitable for a span of time that dwarfs the existence of any animal anyone has ever named. Whether anything used that habitat is another question. We have no fossils from Venus, no surface samples. The few Soviet landers that touched down in the 1970s and early 1980s lasted, on average, less than 2 hours before the heat and pressure killed them. The longest survivor, Venera 13, lasted just over 2 hours. The pictures it sent back show a flat-10 landscape of broken rock under a heavy sulfurous yellow sky. No animals, no plants, definitely no civilizations. But the question isn't whether anything is there now. It's whether anything was 2 billion years ago, when the planet might have looked completely different. Then, somewhere around 700 million years ago, conditions on Venus changed. The trigger is debated. The leading candidates, a massive global resurfacing event that repaved the entire surface volcanically in a relatively short window, maybe 50 to 100 million years. The steady brightening of the sun, increasing in luminosity roughly 10% every billion years. A runaway volcanic outgassing episode that pumped enormous amounts of carbon dioxide into the atmosphere, or more than one of these together. Crossing a threshold the climate could no longer balance. Whatever the trigger, the climate flipped. Water vapor, itself a powerful greenhouse gas, trapped more heat. The hotter atmosphere held more water vapor, which trapped more heat. The oceans began to evaporate. The hotter it got, the more the oceans evaporated. The more they evaporated, the more water vapor entered the air. The more water vapor, the hotter it got. That feedback loop is what scientists mean by a runaway greenhouse. By the time it finished, Venus's oceans were entirely gone. The water vapor in the upper atmosphere got broken apart by solar ultraviolet. The hydrogen, being light, drifted off into space. The oxygen, heavier, mostly bonded with surface materials and locked into rocks. The carbon dioxide that had been dissolved in the oceans and locked in rocks was now free in the atmosphere, and the atmosphere kept thickening. Today, Venus's surface temperature averages about 462 degrees Celsius, 864 Fahrenheit. Hot enough to melt lead. You don't get to stand on it. You'd be dead in less than a second. The surface pressure is about 92 times Earth's. That's the pressure at the bottom of about 900 meters of ocean. Not 900. To find pressure that crushing on Earth, you'd have to go deeper than any crewed submarine has ever taken people. The Soviet landers survived those few hours because they were essentially deep-sea pressure vessels, built with hulls thick enough to handle the weight of an ocean's worth of air. The sky overhead, if you could see it, is a thick yellow gloom full of sulfuric acid clouds. The clouds rain, but the rain never reaches the surface. It evaporates on the way down, because the lower atmosphere is too hot for liquid sulfuric acid to stay liquid. So the sky is weather, and the weather has acid, and the acid never lands. This is Venus now, a place where lead would puddle on the ground, where the air weighs 92 times what ours does, and that air is poisonous, corrosive, full of acid rain that never reaches the surface. A place that is, by any reasonable definition, hell. The way I keep coming back to it is something everyone has done. You put a pot of water on the stove, turn the burner on, walk away planning to come back when it boils. But you get distracted, a phone call, the door, and you forget. When you remember, you walk back into the kitchen, and the bottom of the pot is glowing, and the water is gone. That's Venus. For a long time, the pot was fine. The water simmered. You could still see the surface, still see the bottom. You could still cook in it. Then, Slowly, the water level dropped. Then the pot was dry. Then the pot was glowing. Venus has been a glowing pot for 700 million years, and the burner will not turn off. Here's the part that, for me, makes Venus harder to think about than Mars. The oceans don't completely vanish. They leave a trace. If you measure the ratio of two kinds of hydrogen in Venus's upper atmosphere, you find something that doesn't make sense unless Venus used to have a lot more water. There's regular hydrogen, one proton in the nucleus, and there's deuterium, heavier, a proton and a neutron. Deuterium is rare. On Earth, it makes up about 1 part in 6,400 of the hydrogen in our oceans. On Venus, the ratio of deuterium to regular hydrogen is roughly 150 times Earth's. That's not a small number. It has only one good explanation. Light hydrogen escapes into space more easily than heavy hydrogen because light things move faster at any given temperature, and the lightest things in the upper atmosphere are the ones that get knocked off by solar wind and ultraviolet light. So start with a planet that has both kinds of hydrogen mixed in its oceans. Boil those oceans into the upper atmosphere, and let solar radiation work on that vapor for a few billion years. The regular hydrogen gets stripped away faster. The deuterium hangs around. Over time, the ratio of heavy to light hydrogen in the remaining air goes up. So when we measure Venus's atmosphere today and find 150 times Earth's deuterium ratio, what we're measuring is a chemical fingerprint of an ocean's worth of water that boiled into space billions of years ago. The lighter component carried off first, the heavier left behind. The water is gone. The trace of the water is not. There's a kind of grief in that detail. When you sit with it, we don't usually think of planets as having ghosts, but Venus has one. It's chemical. It's measurable. It's there. The ocean that used to be on Venus is, in a real sense, still hanging in the air, just as a ratio of isotopes, just as a number on a spectrometer, the shape of an absence. We could detect that ratio from Earth with the right telescope 60 light years away. If Venus orbited another star, and we had the right instruments, we could measure the deuterium signature in its atmosphere and say with high confidence, this planet used to have a lot of water, and now it doesn't. Without ever going there, without ever sending a lander, we could read the obituary from a distance. There may be planets out there right now we've already done that with. We just haven't realized what we were looking at. The hardware to measure this reliably across light years is just now coming online, with the James Webb Space Telescope and a generation of extremely large ground-based telescopes arriving in the late 2020s and 2030s. The first time we read a Venus-like ghost on an exoplanet, we won't be making a discovery. We'll be confirming something the universe has been recording on its own, the fingerprint of a former ocean. Venus's porch light is still on. The light's been on for 4 billion years. The house burned down inside. So now we have 2 dead worlds in our own neighborhood. Mars, killed by a cooling core and a vanished atmosphere. Venus, killed by a runaway greenhouse and an ocean's worth of water boiled into space. Different deaths. Same result. 2 planets. Same age, same materials, same construction, same starting conditions. One in the dust, one in the fire, Earth in between, which raises a question that ought to make anyone uncomfortable. How stable is any habitable window anywhere? If 2 of the 3 rocky planets that started inside the sun's habitable zone have already lost their habitability by completely different mechanisms, what does that tell us about the third one? That's where we have to look next. Because, as it turns out, the habitable zone itself is not a place you can plant a flag in and stay forever. It moves. When people first hear about the habitable zone, the image that gets planted is a kind of permanent neighborhood, a ring around a star. Inside the ring, it's just right. Outside, it isn't. The planets inside are the good ones. Earth is inside the ring, and that's why we get to exist. End of story. Almost none of that is right. The habitable zone is real. The math is real. It's specifically the range of orbital distances at which liquid water could, in principle, exist on a planet's surface, given basic assumptions about atmosphere and reflectivity. For our sun today, in the most common estimates, that's the region between about 95% of Earth's distance from the sun and about 170% of it. Different models give slightly different boundaries. But the habitable zone moves. It moves because stars change. Stars look steady to us because human lifespans are short and stars change slowly. But over billions of years, every star brightens, cools, expands, and dies. The brightening part is what matters here. A main sequence star, the kind our sun is, the kind most stars are, gets gradually brighter as it ages. Hydrogen in its core fuses into helium. The core gets denser, pressure and temperature go up, the fusion rate goes up, and the star puts out more energy. Year by year, the increase is invisible. Over billions of years, it adds up. The sun has brightened roughly 30% since Earth formed. That's not minor. That's the difference between a comfortable room temperature and a fever. If the sun today were as faint as it was when Earth was new, the planet would be a frozen ball. There's a paradox built into that. The faint young sun paradox. The sun used to put out much less light, yet there's clear geological evidence of liquid water on Earth's surface as far back as 4 billion years ago. The answer probably involves a much thicker greenhouse atmosphere then, with higher carbon dioxide and methane trapping heat. But the relevant point here is just the brightening. The sun has gotten about 30% stronger over 4.5 billion years, and it's still strengthening, roughly 10% per billion years. That sounds slow. Most things sound slow at that time scale. But applied to Earth's climate, the consequence isn't slow at all. As the sun brightens, the habitable zone moves outward. The distance at which water can stay liquid pushes further from the star. The inner edge, the line beyond which water would boil away under any reasonable atmosphere, creeps outward year by year. Today, Earth sits comfortably inside the habitable zone. The inner edge is somewhere closer to the sun than we are. In about 1 billion years, give or take a few hundred million, depending on the model, the inner edge will reach Earth's orbit. That isn't the end of life on Earth. The mechanics are more complicated. As the sun brightens, the surface warms. The warmer surface evaporates more water into the upper atmosphere. Ultraviolet light breaks that water vapor apart. The hydrogen escapes to space. The same process that played out on Venus. The oceans start to lose water. The surface chemistry changes. The kind of life that needs complex multicellular bodies, stable temperatures, oxygen, and liquid water all together starts to run out of places to live. Most credible models converge on a window of somewhere between 1 and 1.5 billion years from now, before complex life on Earth becomes untenable. Microbes might hang on longer. They can do a lot. There are places on Earth right now where microbial life thrives at temperatures above the boiling point of pure water, inside thermal vents on the ocean floor. Some of that life might survive past the death of multicellular ecosystems. But the kind of planet we live on, forests, oceans, animals, rain, snow, seasons, that planet has roughly 1 billion good years left. Push the timeline further, and it gets worse. In about 5 billion years, the sun exhausts the hydrogen in its core and enters its red giant phase. The outer layers swell outward, hundreds of times its current diameter. Even though the surface temperature actually drops a little, the total energy output goes up by a factor of about 1,000. The inner planet's orbits end up inside the expanding solar atmosphere. Mercury inside the sun, Venus inside the sun, Earth, by the most recent modeling, most likely also inside the sun, somewhere around 7.5 billion years from now. Some scenarios let Earth narrowly survive at the very edge of the red giant's atmosphere, scorched but not consumed. But the central estimate is the Earth gets eaten. So the planet itself has a kind of expiration date, and the habitability of the planet has a different, earlier expiration date. The way I think about the habitable zone is that it isn't a place, it's a moment. I learned a little piano years ago, just enough to make the easy song sound right. And one of the first things you learn is that the keys you can play with one hand are limited. You have an octave, 8 white keys, 5 black, all within reach when your hand is on a keyboard. To play notes outside that octave, you have to move your hand. The habitable zone is the playable octave for liquid water. Within that range, you can do music. The notes work. Water exists in the form that supports life. Outside the octave, the notes are too high or too low, too hot or too cold. The music falls apart, but the piano isn't stationary. Someone is slowly pushing it across the room. Or, if you prefer the actual physics, The playable octave is sliding outward over time. The keys you used to reach keep falling off the edge of the bench. Mars's keys fell off the bench around 3.5 billion years ago. Venus's keys fell off around 700 million years ago. Earth's keys are sitting roughly in the middle of the playable octave right now. The piano keeps moving. The keys keep sliding. There are planets we've found in other systems that may already be past their playable octave, sitting in what we currently classify as a habitable zone of stars that have been around for many billions of years, brightened, and may have already shoved their habitable zone past those planets. We see them, mark them down, and say liquid water could exist there. The truth is more complicated. Liquid water could exist there if conditions are exactly right at the moment we're looking. The conditions a billion years ago might have been very different. The conditions a billion years from now will definitely be different. We're seeing a snapshot. The snapshot doesn't tell us how long conditions have been that way, or how long they'll continue. The habitable zone, in other words, has a built-in time problem we usually ignore. A planet is in the habitable zone now. That doesn't mean it always was. That doesn't mean it always will be. That doesn't mean it ever supported life at any point in its history. The phrase habitable zone carries a sense of permanence the physics doesn't justify. There's a related point worth lingering on. The habitable zone is calculated, in most models, assuming a planet has an atmosphere like Earth's. It assumes a magnetic field. It assumes stable rotation. It assumes water to begin with. None of those are guaranteed. Plenty of planets in the habitable zone have none of them. Plenty of planets that aren't in the habitable zone today might have had all of them in their past. The phrase is shorthand for a much more complicated reality, and the shorthand can mislead. What's true is that the playable range exists for any given star at any given time. What's also true is that the playable range slides over time, and the planets it slides across are different at different epochs in a star's life. A planet that's a perfect candidate for life now might be a frozen wasteland a billion years from now, when its stars dim just enough to pull the habitable zone closer in. A planet that's frozen now might become habitable a billion years from now, as the star brightens enough to thaw it out. The galaxy is full of planets in the wrong place at the wrong time. That's the part that's hard to swallow. There are likely planets out there right now that had their best era a billion years ago and missed everything they could have been. There are likely planets that haven't started their best era yet and won't reach it for another billion years. The number of planets that happen to be in their habitable era right now is a small fraction of the total. We are one of them. The window is open here. The window is closed elsewhere. And that's just our star, a calm, well-behaved yellow dwarf, putting out energy at a steady rate, with few outbursts, lasting a long time. The sun is, by stellar standards, an easy neighbor. Most stars are not like the sun. And most of the planets we found in the so-called habitable zone orbit stars that, on a good day, are merely violent. On a bad day, worse. And on those stars, every day looks like a bad day from a certain angle. That's where we have to look next, because most of the lottery tickets we hold in the search for life are not the kind that pay out the way we imagine. When most people picture a star with planets, they picture our sun, yellowish, steady, even-tempered, throwing off a comfortable amount of light, doing its job without fuss. That's the star you imagine when you imagine alien sunlight on an alien beach. That's not what most stars look like. Roughly 3 out of every 4 stars in the Milky Way are M dwarfs, red dwarfs. Small stars, much smaller than the sun, ranging from about half its mass down to about 8% of it. Cooler, with surface temperatures between 2,400 and 3,700 Kelvin, compared to the sun's roughly 5,800. Because they're cooler, they put out most of their light in the infrared, the visible part leaning red, hence the name. They're dim, they're small. Replace the sun with one, and the inner solar system would sit in permanent twilight. They are also, by a wide margin, the most common kind of star in the universe. 3 out of every 4 stars you could ever visit are red dwarfs. 3 out of every 4 habitable zones being studied are around red dwarfs. 3 out of every 4 announcements of an Earth-sized planet in a habitable zone mean a planet orbiting a red dwarf. So when we talk about how many habitable worlds might be out there, we're mostly talking about red dwarfs by default. The math just works out that way. And that matters because red dwarfs are not gentle. Here's the part that takes a while to absorb. Red dwarfs have a few features that look friendly to life. They burn their fuel slowly, so they live a very long time. The smallest are expected to last trillions of years, far longer than the current age of the universe. They put out steady energy over those lifespans. Their habitable zones are small and tight, so a planet receiving Earth-like amount of energy sits very close to the star, much closer than Mercury is to the Sun. Years are short, a few days to a few weeks. The planets are easy to find because they transit often and block a larger fraction of the star's light. All of that is the good news. The bad news is that red dwarfs are magnetically furious. Smaller stars are more magnetically active than larger ones, especially when young. They produce more spots, more flares. Red dwarf flares can be, in some cases, 10,000 times more powerful than the strongest flare our sun has ever produced. A flare that on the sun would briefly knock out radio across half the Earth would. On a red dwarf, bathe the entire inner system in radiation, no biology, we know would survive without serious shielding. And these flares aren't rare. They're routine. The TRAPPIST-1 system, 40 light-years away, is one of the most studied red dwarf systems we have. 7 Earth-sized planets, several in the conventional habitable zone. On paper, exactly the kind of place we want to look for life. In 2025, JWST observations measured TRAPPIST-1's flare activity over a sustained period and found the star produces roughly 6 flares per day. Every day, that's over 2,000 flares per year, every year, for billions of years. The planets in that habitable zone, orbiting closer than Mercury orbits the Sun, take those flares full in the face, with none of the buffer that comes from distance. They are right next to the speaker. The volume is at maximum. It has been at maximum since the system formed. It will be at maximum for the rest of the star's life, which is to say, for trillions of years. What does that do to a planet? Lab studies have tried to simulate it, exposing Earth microbes, including the most radiation-tolerant one we know, Deinococcus radiodurans, which survives radiation that would kill almost anything else instantly, to the doses of TRAPPIST-1 planets actually receive. The conclusions vary, but the general picture is that flares of this magnitude, repeated this often, sterilize all but the hardiest microbes from any unprotected surface. Anything in shallow water, topsoil, or exposed environments gets cooked. Some life might survive deep underground, in caves, in subsurface oceans beneath ice. But the surface conditions complex life on Earth depends on open sky, running water, photosynthesizing plants, are very hard to maintain on a planet getting hit with that kind of radiation every few hours forever. There's another problem with red dwarf habitable zones: tidal locking. Because the habitable zone is so close to the star, the gravitational interaction between star and planet is strong enough, over geologically short timescales, to lock the planet's rotation to its orbit. The same face always points at the star. The other never sees it. One hemisphere is permanent day, baking under a red sun that never moves. The other is permanent night, cold enough that even atmospheric gases might condense and snow out. The boundary between them, the terminator, is a narrow strip of perpetual twilight. That strip is the only zone where temperatures might allow surface water. A thin ring of habitability on a planet otherwise too hot or too cold to support an ecosystem. Some models suggest a thick atmosphere with the right circulation could redistribute heat from day side to night side, evening things out. Others suggest the day side atmosphere might slowly evaporate, migrate to the night side, and freeze out there, leaving a frozen ocean of nitrogen and oxygen on one hemisphere and no atmosphere at all on the other. Which is right depends on details we mostly don't yet know. The honest answer is that tidally locked habitable zone planets might be habitable in some cases, on the strip with the right atmosphere, with the right luck. Or they might just be split planets, half oven, half meat locker, with a narrow band in between where nothing has time to settle in. So when we count habitable zone planets and land on numbers like tens of billions, we have to be honest about what that means. Most orbit red dwarfs. Most sit closer to their star than Mercury is to ours. Most get hit with flares many orders of magnitude more powerful than any our sun produces, several times a day, for the star's entire life. Many are tidally locked. The phrase habitable zone, applied to these worlds, is doing some heavy lifting it doesn't really earn. I keep coming back to one image. A red dwarf habitable zone is like trying to live inside a boxing ring, while an opponent 4 times your size throws a haymaker at you every 4 hours. For your entire life, for billions of years, you might still be standing. You might even be conscious. There might still be a body in the ring at the end of the round. But the word habitable is doing some heavy lifting in that sentence. Because whoever is standing has spent a lifetime taking blows that would have flattened most of the population by the 3rd round. That's most of the lottery tickets we have. 3 out of every 4. Most of the candidates for life we're currently studying are sitting inside a fight that never ends. There are exceptions. Older red dwarfs whose magnetic activity has settled. Planets around K dwarfs and G dwarfs like our sun. But those are less common, harder to find, and not where most observations point. The Porch light is still on a round TRAPPIST. 1. It flickers 6 times a day. The bulbs are unstable. The wiring keeps tripping. Every time you think you're about to see the house, the porch goes dark. Then the surge comes back and the light flares so brightly that, for a moment, you can't see anything else. That's what most of the lottery looks like. So we now talked about a lot of dead worlds. Worlds where the conditions left. Worlds where the star never let them settle. Worlds in the wrong era of their star's life. Worlds whose habitability is a moving target pushing past them. It's worth pausing here. Because so far we've been talking about other people's deaths, other planets, other systems, other stars. The harder question is what Earth's own history looks like. Because Earth, the planet we treat as the steady one, the one that worked, has more endings in it than most people realize. The lights almost went out here, repeatedly, and once. They almost went out because life itself learned to do something it had never done before. The standard story is that we got lucky. The sun is calm, the orbit stable, the moon steadies our axial tilt, the magnetic field holds, the atmosphere holds, the water holds. Life showed up, stuck around, and here we are. That story is true in its broad outline. Earth is, by every measure, an unusually steady world. We've had 4 billion years of conditions that let life keep going without ever fully resetting. That's not nothing. That's the biggest thing. But it's not the whole picture. Earth has come very close to going dark more than once. The fossil record contains evidence of 5 major mass extinctions, plus a long list of smaller ones. Events where so much of the world's biological diversity died off in a geologically short window that the fossil record itself becomes thin. You can read the geological summary of a mass extinction in a single afternoon, even though the recovery took millions of years. There's just as much to say. The fossils stop, the pollen stops, the microfossils stop, the carbon ratios in the rocks change, the lights for a moment go out. The 5 are the Ordovician, Silurian, around 444 million years ago, taking about 85% of marine species. The late Devonian, around 372 million years ago, taking roughly 75% of species. The Permian, Triassic, around 252 million years ago, the worst one we know. The Triassic, Jurassic, about 201 million years ago. And the Cretaceous, Paleogene, 66 million years ago, the one with the asteroid and the dinosaurs. The Permian, Triassic, is the one that ought to make anyone uneasy. It's sometimes called the Great Dying. Roughly 96% of marine species died. Roughly 70% of terrestrial vertebrates died. Insects, notoriously hard to kill, had the only mass extinction in their history. The fossil record on either side of that boundary looks like 2 different planets. Almost nothing made it across. The trigger, by the best current understanding, was a massive series of volcanic eruptions in what's now Siberia, pumping enormous quantities of carbon dioxide and sulfur compounds into the atmosphere, acidifying the oceans, lowering ocean oxygen, and warming the climate by something like 10 degrees Celsius in a relatively short window. It took the planet between 5 and 10 million years to fully recover ecological complexity. 5 to 10 million years where life on Earth was, in some genuine sense, on life support. That's the worst one in the fossil record. But it's not the worst extinction event Earth has ever been through. The worst one happened so long ago that it almost doesn't have a fossil record. It happened to single-celled organisms in shallow seas, more than 2 billion years before any of the famous extinctions. It's called the Great Oxidation Event, and it's the strangest catastrophe in the planet's history, because it wasn't caused by an asteroid or a volcano or a comet. It was caused by life itself. Here's how it went. For about the first 2 billion years of life on Earth, the dominant organisms were anaerobic. They got their energy from chemistry that didn't involve oxygen, because there wasn't any free oxygen to use. The early atmosphere was mostly nitrogen, carbon dioxide, methane, water vapor, and a few trace gases. Oxygen wasn't on the list. It's highly reactive, and there was nothing around making it in significant quantities. The bacteria and archaea of the early Earth used chemistry we'd find profoundly strange. They oxidize hydrogen, sulfur compounds, iron compounds, methane. They lived in deep ocean vents, shallow tide pools, stratified water columns. They were the entire biosphere for about 2 billion years. Then one group of bacteria, the ancestors of today's cyanobacteria, evolved a new trick: photosynthesis using water as the electron donor. In plain terms, they figured out how to use sunlight, water, and carbon dioxide to build sugars, and as a byproduct, they released oxygen. Free oxygen. Pure O2. It started slowly. The early oxygen mostly got eaten up by reactions with dissolved iron and other reduced compounds in the oceans. For a long time, there was what geologists call an oxygen sink. The oxygen was being produced, but the oceans absorbed it almost as fast as it came out. There's evidence in the rock record. The banded iron formations, those layered red and dark sediments found in places like Western Australia and northern Canada, are the fossilized fingerprint of that process. Alternating band of iron oxide and silica deposited as dissolved iron precipitated out in response to rising oxygen. Each band is a chapter in a story about life slowly poisoning the chemistry of its own oceans. Eventually, the sinks filled up. The oxygen had nowhere to go but up. It started accumulating in the atmosphere around 2.5 billion years ago, with the Great Oxidation Event itself, the clear geological marker, dated to about 2.4 billion years ago. For most life at the time, that was a catastrophe. Oxygen, for an organism that evolved without it, is a poison, a reactive molecule that tears apart cellular chemistry. The anaerobic microbes that had spent 2 billion years building the entire biosphere weren't equipped for it. The rise of atmospheric oxygen, slow in geological terms, fast in evolutionary ones, killed off something like 80 to 99% of life on Earth at the time. The number is hard to pin down because the fossil record that far back is thin, but the genomic and chemical evidence converges on a catastrophe of unprecedented scale. The first true mass extinction in the planet's history wasn't caused by a rock from space. It was caused by life learning to do something it had never done before. The first mass extinction was the air we now require to breathe. I want to sit with that for a second. Everything you've inhaled today is part of the same atmosphere that, 2.5 billion years ago, was a planetary disaster. The oxygen you need to keep your brain working is the same molecule that exterminated most of the biosphere the first time it showed up at high concentrations. It was a poison in its day. It became a fuel later, after enough organisms evolved to handle it. The reason multicellular life is possible at all is that oxygen is energetically rich, and animals like us have metabolisms that can extract a lot of energy from it. None of that would have happened without the Great Oxidation Event. None of it would have happened without life nearly killing itself. The recovery took a very long time. Between the Great Oxidation Event and the first complex multicellular organisms in the fossil record, there's a stretch of about 1 billion years where the geological evidence is famously dull. Paleontologists call it the boring billion. Not much is going on in the rocks. Microbial life is around, quiet, catching its breath. The biosphere has been knocked back so hard it spends 1 billion years just getting reorganized. Eventually, single-cell life learns to use oxygen efficiently. Eventually, eukaryotic cells appear with their internal organelles and complex chemistry. Eventually, multicellular life appears. Eventually, animals show up, but the gap between the catastrophe and the recovery is enormous. The planet, in a real sense, almost stopped breathing 5 separate times. And once, the breathing itself was the thing that almost killed it. The atmosphere we now require to live is the same atmosphere that, when it first appeared, was an extinction event. That should change how you think about life on Earth. The picture of Earth as a stable, life-friendly planet is true, but only in the broadest sense. Yes, the planet has supported life continuously for about 4 billion years. Yes, conditions stayed within a range life could keep finding niches inside. But within that broad continuity, there have been at least 5 major resets, plus the largest reset of all, the oxygen catastrophe. Almost everything alive has died multiple times, in different ways, for different reasons. The thread of life on Earth is not a thick rope. It's a series of thin filaments. Some broke, some survived. The surviving ones carried everything forward, each time. The relevance of the question of life elsewhere is straightforward and unsettling. If life on Earth, on the planet we're calling the success story, has almost been wiped out multiple times, and once was nearly wiped out by its own metabolic byproducts, what are the odds life elsewhere navigated similar transitions successfully? What are the odds a young planet somewhere evolved photosynthesis, then choked on its own oxygen and never recovered? What are the odds a planet developed a powerful volcanic episode, or a glaciation, or an atmospheric shift, and the recovery never happened? We have one example of life that survived its own evolution. The fact that we exist means it can happen. The fact that it almost didn't, on the only example we have, means it might fail more often than it succeeds. That's a hard thing to know about your own planet. Earth nearly went silent. The fossil record gets thin enough, in places, to read in a single afternoon, all of which raises a different question. We've been talking about what happens to life once it gets going. We haven't talked about how often life actually gets going in the first place. And it turns out that's a question we don't have a good answer for either. We have exactly one example, and one example doesn't tell you much about how common the thing actually is. There's a tendency, when we talk about habitable planets, to assume habitability and inhabitation are the same word. They are not. They are not even close. Habitability is a description of conditions. Inhabitation is a description of what's actually living there. The first is a kind of resume. The second is whether anybody ever showed up to do the job. Here's what we actually know about life starting on a planet. We know it can happen because we're on a planet where it happened. That's one data point. That's the entire data set. We don't know how often it happens when conditions allow it. We don't know if it always happens given enough time or usually fails. We don't know how to tell from outside a planet whether life ever appeared in it. We have hints. We don't have answers. What we do know is this. Earth had liquid surface water for somewhere between 100 million and 700 million years before there's any clear evidence of life. That's the gap between the planet being habitable and the planet being inhabited. On the only world we know that is both, estimates of when Earth's oceans first stabilized as liquid water range from about 4.4 billion years ago to about 4 billion. Estimates of the earliest convincing evidence of biological activity range from about 4 billion to about 3.5 billion. So somewhere between 0 and 700 million years passed between Earth being capable of supporting life and Earth actually having it. That gap matters because we don't know what happened during it. Was life almost instantaneous? The apparent gap just an artifact of an incomplete rock record? Or did it take 500 million years of chemistry running and rerunning before the first self-sustaining biological system took hold? The answer would tell us more than almost anything else about whether life is common in the universe or vanishingly rare. The trouble is, we don't know. The earliest fossils are debated. The earliest biosignatures, depleted carbon isotope ratios that metabolism tends to produce, are debated. The earliest microbial mats, called stromatolites, are debated. The earliest direct evidence of cells is debated. Papers refine these dates every year in both directions, and the field doesn't settle. The honest answer is that life on Earth got started somewhere between very quickly and very slowly, and we can't tell which. What we can do is look at how complicated the first step actually is. The transition from non-living chemistry to a self-sustaining, self-replicating, evolving cell is a hard problem to define, let alone solve. You need information storage, DNA, RNA, or something equivalent. You need a way to translate that information into action, proteins, or their equivalents. You need a way to enclose the system, a cell membrane. You need an energy source. You need a way to make copies imperfect enough that variation accumulates, but accurate enough that the system doesn't fall apart. You need all of that working together on a planet where it is time to assemble. None of that is trivial. There are biochemists who think the assembly of the first cell is a problem so hard it might happen only once in a lifetime of an entire galaxy, by sheer chance. There are biochemists who think it's so favorable it should happen on any planet with the right chemistry within a few million years. Both groups are smart. Both work from the same evidence. They disagree because the problem is genuinely hard and the evidence genuinely thin. A good way to think about it is the difference between dropping a seed on bare stone and dropping a seed in good soil. Drop a seed on bare stone, and you can be pretty sure nothing will come of it. The conditions aren't right. The seed sits there. That's most of what we found in the Exoplanet catalog. The conditions are wrong. Whatever happened to the seeds, they didn't grow. But here's the part that takes a minute to absorb. Even if you drop a seed in good soil, you don't automatically get a tree. You might get nothing. The seed might be the wrong species. It might be old. A bird might eat it before it germinates. The soil might be good in all the ways you tested, but subtly wrong in some way you didn't check. Conditions in good soil are necessary, but not sufficient. The seed has to actually take. Habitability is the soil. Whether anything showed up to grow in that soil is a separate question, and not one we know the answer to in any general way. The universe is dropping seeds across hundreds of billions of planets. We don't know what fraction germinate. We have one example of a tree, and no idea whether the field is full of other trees we just can't see, or mostly empty soil with one tree standing in it. Mars is the most painful case to think about, because it sat there with everything it needed for a long stretch of time, and we still can't tell. Mars had liquid water for hundreds of millions of years. It had an atmosphere, a magnetic field for a while, the chemistry, the energy sources, volcanic activity, hydrothermal systems. By every measure we can apply from a distance, Mars should have been able to support life in the same era life was getting started on Earth. Did it? We don't know. We have a tube, we have a rock with patterns in it that, on Earth, would be a textbook microbial biosignature. We have the careful language of the people who published the analysis, the language of suspicion, not confirmation. And we have, at the time of recording, no way to bring that tube home, with the retrieval schedule stretched into the late 2030s, possibly later. Even if we retrieve it, even if it comes back, even if lab analysis confirms, beyond reasonable doubt, that the rock contains traces of biological activity from 3.5 billion years ago, that gives us a second example. 2 planets in one solar system where life appeared. From 2 examples, we still wouldn't know the rate at which life appears in the universe in general. We'd have a much better estimate. We'd have made one of the most consequential discoveries in the history of our species. But we'd still be talking about a single solar system. Venus is even worse. Venus may have had liquid oceans for 2 to 3 billion years. We can never check, in any meaningful sense, whether anything lived in those oceans. The surface of Venus today, with its acid clouds and lead melting temperatures and crushing pressure, is not a place that has preserved any biological record from the planet's temperatures, and crushing pressure is not a place that has preserved any biological record from the planet's habitable past. Whatever fossils Venus might have had, if it had any, have been baked, crushed, and chemically erased. Some of the most ambitious mission concepts involve atmospheric probes that could float in the upper cloud decks, where temperatures and pressures are closer to Earth-like. There's even speculation about whether microbial life could survive in Venus's cloud layer today, in the temperate zone about 50 kilometers up. But those are speculative searches. The historical record is gone. Then there are the worlds we haven't even talked about. Europa, Jupiter's icy moon, with a subsurface ocean of liquid water beneath a frozen shell maybe 20 kilometers thick. Enceladus, one of Saturn's moons, shooting plumes of water vapor into space from cracks in its ice-covered surface, indicating an internal liquid water ocean. Titan, Saturn's largest moon, with a thick atmosphere, lakes of liquid methane, and the possibility of exotic chemistry that might be a different kind of life entirely. There are places in our own solar system where conditions exist for some kind of biology. We've barely begun to check. And then there are the exoplanets. 6,000 confirmed. Hundreds of billions estimated. Even with the most ambitious telescopes we can imagine, we will almost certainly never directly sample any of them. The light from those planets, after traveling light years to reach us, can be analyzed for atmospheric composition. We can look for water vapor, for oxygen, a possible sign of photosynthesis on a rocky planet, for methane, for combinations of gases that wouldn't naturally coexist in equilibrium, which would suggest something is actively producing them. That's the toolkit. It's powerful, but it's a toolkit for reading fingerprints in air, not for sending a tube down to the surface and bringing it back, even with the best instruments we'll ever have. We may detect candidate biosignatures on dozens of exoplanets in the next few decades. We will probably never confirm them by going there. We'll be in the position we're in with Mars, multiplied by hundreds, a rock we can't reach, a signal we can't follow up, a possibility we can't close. There's a thought experiment that helps me think about this. Imagine an alien astronomer, somewhere out there, studying our solar system from a few hundred light years away. They have powerful telescopes. They can detect the orbital signatures of all 8 planets, measure the atmospheres of the rocky ones. They look at Earth and see oxygen, water vapor, methane, ozone, signatures that, by their best models, look like a biosphere. They write a paper. They publish a finding. They put Earth on the candidate list. What they cannot do is come here. They cannot send a probe. They cannot bring back a sample. The distance is too great. They will know Earth probably as life. They will not know what it looks like. They will never confirm it. They will spend the rest of their civilization's existence with Earth as a marker on a chart, an item on a list of candidates, a possibility they can't close. That's where we are with the 6,000, with the eventual 60,000, with the hundreds of billions. We will compile a list. It will be partial. Some entries will be correct. Some will be false positives. We will rarely have the luxury of finding out which is which. And the Mars tube, the one we drilled in July 2024, the one we may not retrieve until late 2030s, is the closest we will ever come to a real sample. That's it. That's the one. We have one tube. We can't get to it. Every other candidate world is much farther away, and the tube is the high water mark. The most consequential rock in our possession is sitting on the surface of another planet, in a metal cylinder in the wind, and we may or may not be able to bring it home before the people who drilled are retired, which means that when we look up at the sky and try to figure out who is or isn't out there, we have to be careful about what we're actually looking at, because what we see from down here is not a snapshot of the universe as it is right now. It's a different thing, and once you see the difference, it's hard to unsee it. That's where we have to look next. When you walk outside at night, somewhere dark enough to actually see the stars, what you're seeing is not the sky. You're seeing a record. Every point of light you can pick out with the naked eye, binoculars, or a telescope is light that's been traveling at the speed of light for some amount of time before it hit your eye. The sun you see is 8 minutes and 20 seconds old. The moon is a little over a second old. The brightest star in the night sky, Sirius, is about 8.6 light years away. The light hitting your eye left it 8.6 years ago. Whatever Sirius is doing right now won't reach Earth for another 8.6 years. Light is fast. Astronomically, light is slow. Proxima Centauri, the nearest star to the sun, is 4.24 light years away. The light you see left in 2021 or 2022. The North Star Polaris is roughly 430 light years away. The light you see tonight left when Galileo was still alive, maybe before. The brightest visible stars are mostly within a few hundred light years. The faintest naked eye stars stretch to several thousand. The light from the center of the Milky Way, a faint smudge on a dark night, left the galactic center about 26,000 years ago. The light from the Andromeda Galaxy, the only other major galaxy you can usually see without a telescope, has been traveling for about 2.5 million years. It left when our ancestors hadn't invented agriculture, or language as we recognize it, or really anything. Andromeda's light is older than humanity. Then there are the galaxies JWST has been finding at the edge of the observable universe. The most distant ones sent their light out when the universe was less than 5% of its current age. That light has been traveling for more than 13 billion years. The galaxy that sent it has changed in ways we can't measure. It might still exist in some form. It might not. Whatever shape it's in now, we have no way of seeing the current version. Only the version from 13 billion years ago. So when you look up at the sky, you are, in a real sense, looking at history. Everyone has heard that this is technically true. What it means to actually live in a universe like this is harder to absorb, because what it means is that the night sky is a postal system. Each point of light is a letter. The letters were mailed at different times. They arrived at your eye all together at this moment, but they weren't sent at the same time. Some were sent yesterday, some 1,000 years ago, some during the Roman Empire, some before any of our ancestors stood upright. A few were sent by senders who, by the time the letter arrived, no longer exist. That last one is the part that takes a minute. Stars die, not often in human terms, but constantly in galactic ones. There are stars in the night sky that, somewhere in the past few centuries or millennia, have ended, run out of fuel, collapsed, blown off their atmospheres, become white dwarfs or neutron stars or black holes. The transition can be slow, a small star fading into a remnant, or fast, a supernova. Either way, the star you see now is not the star that's there now. The star you see now is a memory. The light is still traveling, will be, for years or centuries or millennia after the star itself is gone. There is, somewhere in the visible sky, at least one star whose light is on its way to your eye right now, even though the star came from no longer exists in any form we'd recognize. You can't tell which one. You can't tell from the envelope. The letter looks the same as the one from senders still very much alive. You only know that some of them are from senders who aren't. The sky we see is, in a real sense, a memorial. I want to push that further, because it connects to everything tonight. Every habitable planet we've detected, or might detect, is also a letter from the past. The light from a planet 50 light years away is 50 years old by the time it reaches us. The atmospheric composition we measure is 50 years out of date. A planet 100 light years away, 100 years out of date. A planet 1,000 light years away, 1,000 years out of date. That doesn't sound like much for a planet. Atmospheric composition changes slowly. A few hundred years on a world that's been around for billions shouldn't matter much. And mostly it doesn't. But when we get to the edge of what we can detect, or when we ask whether a specific planet is currently inhabited, the time lag matters. The light from a planet 10,000 light years away tells us what its atmosphere looked like 10,000 years ago. Civilizations rise and fall in less than that. If a technological civilization existed there for, say, 5,000 years and then collapsed, and the collapse happened 9,000 years before the light we're seeing left them, we might be looking at light from a still active civilization. If it had collapsed 11,000 years ago, we'd be looking at light from after they were gone, and we'd see no signature of them at all. Whether anyone is out there right now is a question we cannot directly answer. We can only ask whether anyone was out there at the moment the light left them. We cannot ask about now. Now, applied to a star system thousands of light years away, doesn't have meaning in a way we can investigate. Now is a local concept. The universe doesn't really have a global now. So when we look up and try to figure out who is or isn't out there, we are, in a real sense, opening a mailbox full of letters of different ages, from different senders, with no return address, and dates we can't fully trust. Some are from people still home, some from people who moved, some from people who died long before the letter arrived. We sort through them. We do our best. We make our maps. The maps are useful. They are also, fundamentally, maps of a place that may or may not still exist in the form the map describes. This connects to the harder thing, the thing we've been circling all night. The universe might not be empty. It might be a graveyard. Many of the lights you can see could be coming from places where life happened and then ended long before that light started its journey toward you. The deaths could have happened so long ago that the news hasn't reached us yet. The news is on the way. 50 light years out, or 100 or 1,000. Traveling at the only speed information can travel through this universe. We will get the news. We won't know when. We'll see a star, measure its planet, find a signature that looks like life. The signature will be a fingerprint from a planet that may not have had life for a long time by the moment we're measuring it, and we won't be able to tell. The honest version of stargazing, the one that takes the physics seriously, is that we are reading mail. Some of it is recent, some of it is old, some of the senders are still home, some are not. The mailbox is enormous. The letters never stop arriving. You can spend a lifetime sorting through them. You'll never finish. There's a particular feeling that comes with this. Late at night, when you let it sink in, you step outside. You look up, you find a bright star, and let your eye rest on it. You think about the years that light has been traveling. You think about what was happening on Earth when it started its journey. You think about what was happening on the planet that sent it. If there was a planet, if there were inhabitants, what they might have been doing on the day that particular photon left them on its long trip across the dark. And then you realize a photon is just one photon, out of trillions arriving at your eye every second. Every star is sending letters, constantly. The mailbox is full beyond comprehension. Every glance at the sky is a glance at more mail than you can ever read. Some of it is from senders who are still alive. Some of it isn't. You can't tell the difference. Not from down here. Not yet. Which leaves one last thing we have to talk about. The one part of the sky we can actually do something about. The one we're standing on. There's an instinct when we talk about all this to position Earth as the exception, the one that worked, the lucky planet, in the lucky orbit around the lucky star, with the lucky moon, the lucky magnetic field, the lucky atmosphere, the lucky biology. Everything broke our way. We get to sit here, for a billion years into this, breathing the same air that almost destroyed the biosphere when it first appeared, looking up at planets that didn't make it, and feeling, on some level, that we are not on the same list as them. We are on the same list as them. Earth is not the exception. Earth is the one in the middle. Earth is at the part of the story where the lights are still on, but the timer is running. The fact that we exist at this particular moment is not because Earth is a different kind of world than Mars or Venus. It's because we showed up at the right time. We are inside a window. The window is open right now. The window will close. Let me lay out the numbers, because they're specific, not abstract. Earth formed about 4.5 billion years ago. Liquid water on the surface goes back at least 4 billion, possibly 4.4 billion. Life shows up in a rock record somewhere between 3.5 and 4 billion years ago. Complex multicellular life, around 600 million years ago. Animals with hard parts, around 540 million. The first land plants, around 470 million. The dinosaurs, between 230 and 66 million years ago. Modern humans, about 300,000 years ago. The agricultural revolution, about 12,000 years ago. Modern industrial civilization, about 200 years ago. That's the history. That's where we've been. Now look forward. The sun, as we talked about, has been brightening roughly 10% per billion years. The brightening continues. Multiple lines of evidence converge on a window of somewhere between 1 and 1.5 billion years from now, before conditions on Earth become too hot for complex multicellular life to keep functioning. That doesn't mean the planet becomes uninhabitable instantly. It means a slow process of warming, evaporation, atmospheric loss, and oxygen decline crosses a threshold past which the ecosystems we recognize can't keep going. The oceans will be evaporating. The plants that need stable temperatures will struggle. The food chains that depend on them will struggle. The animals at the top, including any version of us, will be in trouble. Microbes might hang on past that point. There are organisms on Earth right now that thrive in conditions that would kill almost everything else. In deep rock, superheated water, subsurface aquifers. Some of that life might continue for hundreds of millions of years after the surface becomes uninhabitable for everything else. Earth's biological history might end with the same kind of organisms it started with, microbes in the dark, quietly carrying on in environments that no longer have a sky worth looking at. That's the first phase of the ending. Sometime between 1 and 1.5 billion years from now, the surface stops being a place for complex life. The biosphere collapses. The oceans begin to disappear. The same kind of processes that played out on Venus, on a different timescale, through a different mechanism, begin to play out here. In about 3 to 4 billion years, The surface temperature is high enough that the oceans are essentially gone. The atmosphere is thinning. Carbon dioxide is climbing. The planet is in slow motion, becoming a hotter, drier, more hostile version of itself. Plate tectonics depends on water at the surface and the crust. And as the water leaves, the geology grinds to a halt. Earth, by this point, would not look anything like the Earth we know. The continents would still be there. The mountains would still be there. The oceans would not. In about 5 billion years, the sun runs out of hydrogen in its core and begins its red giant phase. The outer envelope expands. Mercury is swallowed. Venus is swallowed. By the most recent modeling, refined in the last few years to account for solar mass loss and tidal interactions, the central estimate is that Earth ends up inside the expanding sun. Some studies suggest Earth's orbit might migrate outward enough to escape, leaving a scorched, airless rock circling a slowly cooling red giant. Others suggest orbital drag from the expanded solar atmosphere pulls Earth inward and consumes it. The central estimate, for what it's worth, is that Earth doesn't make it. The likely engulfment timeline is somewhere around 7.5 billion years from now. So here's the full window. Earth has been habitable for approximately 4 billion years. Earth will be habitable for approximately 1 to 1.5 more billion years. The total window of habitability, start to finish, is somewhere between 5 and 5.5 billion years. We are demonstrably past the middle. I want to say that one more time, because it's the part that's hard to hear and easy to skip. Earth's total window of habitability is about 5 to 5.5 billion years long. We are currently around 4 billion years into it. We have somewhere between 1 and 1.5 billion years left. The largest portion of Earth's life-bearing history is behind us, not ahead of us. That's not a doomsday claim. It's not next week. It's not in any time frame that should affect any decision any human being makes about anything in their actual life. 1 billion years from now is so far in the future that the continents themselves will have rearranged into shapes nobody alive today would recognize. Whatever exists on Earth in 1 billion years will be as different from us as we are from the first eukaryotic cells. The species we are won't be here. The civilization we have won't be here. The languages we speak won't be here. But the planet's own trajectory, the long arc of the planet itself, is past the middle. Earth is not in its morning. Earth is in its late afternoon. The evening hasn't started yet, but it will. The window is open. The window won't be open forever. That's the third unsettling thing I wanted to leave you with. Not because it's frightening. It's just true. Earth is not, in the long arc of itself, the exception. Earth is the one currently demonstrating what habitability looks like in the part of the story where it's actually happening. Mars showed us what comes after. Venus showed us what comes after a different version of after. Earth is showing us what during looks like. The during is the whole point. The during is what makes the universe interesting when it happens. The during is rare, by our best guess, both in space and in time. Earth's atmosphere in the far future will go through its own escalation and eventual loss. Different mechanism than Mars, but the ending rhymes. The sun brightens. The upper atmosphere heats. Water vapor gets transported high enough that ultraviolet light breaks it apart. The hydrogen escapes to space. The oxygen gets sequestered into rocks or burns off. The atmospheric pressure drops. The magnetic field, depending on the future evolution of Earth's interior, may or may not weaken at the same time. The end state of Earth, in 3 or 4 billion years, looks like a less extreme version of Mars or a less extreme version of Venus, depending on which physics wins. Either way, the destination is similar: a dead world, with a thin or absent atmosphere, no liquid surface water, no biosphere, orbiting a star also nearing the end of its main sequence. Remember how Mars lost its atmosphere. The shield went down. The wind picked at the air. The pressure dropped. For hundreds of millions of years, Mars, in a real sense, is what Earth is in the process of becoming, just along a different timeline. Mars was a dead other when we started tonight. Mars is also the preview. The way I've come to think about all of this is as a long evening. The day is over. The evening is here. The light is still warm. The window is still open. The night is coming, but the night is not here. We get to sit on the porch of this planet while it's still possible to sit on the porch of this planet and watch the sky and read the letters and try to figure out who else, somewhere out there, might also be sitting on a porch while their light is still warm. The window won't stay open. That's true. It's also true that the window is open now. Both things are true at the same time. The thing about a window being open is that what matters is whether it's open in the moment you're standing in. Earth's window is open. The oceans are still liquid. The air is still breathable. The magnetic field is still up. The planet is still doing the work of being a planet that supports life. None of that is broken. If I had to choose an image for this part, it would be the feeling you have on a particular kind of evening. The kind where the air is finally cool after a hot day, where the light is going golden, where you know it's going to get dark, but it isn't dark yet, where you can sit outside and not feel cold and not feel hot, and the world is doing its small, ordinary things around you. That kind of evening doesn't last. It can't. The dark is coming, but the dark isn't here. That's the moment we live in. Earth is having one of those evenings. The evening is several 100 million years long. We get to be inside it for a sliver of that span. The evening is good. The evening is warm. The evening is going to end. None of those facts cancel each other out. There's something genuinely strange about being the species that figured out the timeline. None of the other animals on this planet have any idea this is happening. The dolphins don't know. The crows don't know. The trees don't know. Only we have done the math. Only we have looked at the rock record and the stellar physics and worked out with mathematical specificity where we are in the long arc of our own world. That knowledge is recent. People have only known this with anything like the precision we have now for a few decades. Most people don't know yet. Most people still imagine Earth as a steady, permanent thing. You knowing it is part of why this matters. Because once you know, the night sky becomes something different. The porch light becomes something different. The question of whether anyone else is out there becomes something different. It becomes less a question of how many neighbors we have, and more a question of which ones still have their light on, and which ones used to, and which ones never did, and which ones might be reading their own version of the sky right now, looking back at us, wondering the same things. The porch light is still on here. For now, I want to spend a little more time in the place we've arrived at before we close the night, because the texture of it matters. The shift in how you see the sky is the actual thing this whole conversation is about. The facts are scaffolding. The shift is the building. When you absorb that most habitable windows close, and that most stars are not gentle, and that most planets are nothing like ours, and that even ours is well past the midpoint of an arc, you stop seeing the night sky as a question about who might be out there. You start seeing it as a question about when. When did the conditions arrive on each of those worlds? When did they leave? When did anything take advantage of them? Are any of those worlds doing, right now, what Earth is doing right now? Are any of them somewhere in their own equivalent of a long evening, also looking back across the dark at lights that may or may not still have someone behind them? That's a different way to think about the sky. Less a search for company, more a survey of times, some of which overlap with ours, most of which don't. The galaxy, in this picture, isn't a city of neighbors. It's something more like an archive of moments. Each star and each planet is its own slice of time, with its own beginning, its own duration, its own end. The slices don't usually line up. The galaxy is full of lives that started before us, ended before us, started after us, will end after us. We're walking through the archive. We can't see most of it. We can only see the slices whose light happens to reach us now. And we can only act on the ones we can study with the tools we have. That's not depressing. When you sit with it long enough, it's actually clarifying. The standard framing, either we are alone or we are surrounded, is a binary that doesn't really fit the universe we live in. The real situation is that we are inside a moment, and other moments have happened, and other moments will happen. And the question of whether we have company isn't about presence or absence in some absolute sense. It's about overlap. The overlap is what we never have a great instrument for. Time is harder to measure across light years than distance. A star's spectrum tells you what it's made of and how hot it is. A planet's transit signature tells you how big it is and how close it is. The atmospheric spectrum, if we can measure it, tells you what the air is made of. None of those tells you when, in the planet's own history, the snapshot was taken. You're always looking at a moment. You're always missing the timeline, which means the question of whether the universe is empty has a quiet answer we don't usually consider. The universe might be empty in the sense of right now. The universe might be full in the sense of all time. Both can be true at the same time, depending on how you take the snapshot. And the snapshot we get to take is the one available from our position, with our instruments in our particular slice of time. Here's what I find myself coming back to late at night. The fact that there have probably been worlds where life appeared, lasted for some span of time, and ended is one of the most quietly profound things our species has worked out. It's a sentence that wasn't really sayable in any rigorous form until the last several decades. Before then, you could speculate, write science fiction, imagine. You couldn't really argue it from a physics. Now we can. The physics doesn't quite force the conclusion, but it now supports it strongly enough that you can build a coherent picture out of it. Worlds happen, then they stop happening. The universe is in the business of producing places where the lights come on, run for a while, and go out again. Some of those places, on the few we've gotten close enough to study, may have had life. Some may have had nothing. Some may have something right now, in their local now, that we won't know about for 1,000,000 years. Because the light hasn't reached us yet. That's the universe. That's what's actually out there. The night sky isn't a void. It isn't a crowd. It's an archive of long evenings, in different stages of the same long story, with our particular evening currently happening here. There's something else I want to say, because it's been sitting with me through this whole conversation, and it's the part that doesn't make it into most of the science. The fact that Earth is past the middle doesn't change anything about how good the evening still is. The evening is still warm. The kitchen window is still lit. The voices inside the house haven't stopped. The seasons still come. The rain still falls. The stars still come out at night. Whatever's coming is coming. Tonight isn't that. Tonight is one of the nights inside the open window that, if you've been listening this whole time, you might have started to feel a particular kind of quiet settle in. That quiet is not pessimism. It's not optimism either. It's something else. It's what you get when you let the actual scale of the situation arrive, without trying to make it into something more comforting or more frightening than it is. The universe has been running for 13.8 billion years. The Earth has been around for 4.5. Life has been around for 4. We've been around for 300,000. Civilization for 10,000. We're a sliver of a sliver. The slivers before us are gone. The slivers after us aren't here yet. The sliver we are inside is the only one we get to experience directly. And the sliver is warm, right now, tonight. I think that's the closest I can come to saying what this is actually about. It's not about being scared. It's not about being awed. It's about noticing where you are. Earth, in this moment, is doing a thing planets only get to do for a thin slice of their existence. It's hosting life. It's supporting weather. It's holding an atmosphere. It's keeping water liquid. It's spinning at a stable rate. It's protecting itself with a magnetic field that's still up. It's giving us the kind of night where you can step outside and see the sky and not freeze and not boil and not suffocate. That's the gift. That's the only gift the universe ever gave us. Everything else is a consequence of that gift. Mars used to have something close to this. Venus had it for longer. Both of them lost it. The mechanism was different in each case, but the result was the same. The window closed. The lights inside went out. The porch lights are still on, in the sense that the sun still shines on those worlds. Nothing else is on. The houses are dark. We've been knocking on Mars for 60 years. We've barely begun to knock on Venus. We will probably never knock on most of the other worlds. The knock takes too long. The distance is too great. The instruments are still being built, but there's a knock we can hear right now. The most useful knock of all. And it's the one that has nothing to do with other worlds. It's the one coming from this one. The wind, the trees, the rain on the roof, if you're somewhere where it rains. The breathing of the person beside you, if there's a person beside you. The hum of a refrigerator, the distant sound of a road, the clock ticking. Whatever's making any noise in your room right now is the sound of a planet that's still alive. That sound has been continuous, in some form, for 4 billion years. The sound is the gift. The sound is what we mean by habitable. The sound is going to stop eventually. Not for you, not for anyone you'll meet, not for any version of any civilization that any human will ever build. But in the long arc, it's going to stop. The planet will go quiet. The wind will keep blowing for a while after that. But it'll be moving a different atmosphere on a different planet that just happens to have the same name. The continuity won't be biological. It'll be just geological. The rocks will remember us in some form, in fossils that may or may not be readable by anyone or anything. We will become the layer in someone else's deep history. That's all eventual. It's not now. Now, the porch light is still on. The kitchen is still warm. The window is open. That's where I want to end the long part of the night. With the window open, with the porch light on, with the gift still going. There's one last thing I want to say before we close, and then we'll be done. If you stay with me this far, you've heard about Mars and Venus, and worlds you will probably never set foot on. You've heard about life killing itself by learning to breathe. You've heard the strange and very quiet fact that Earth, the warmest house in the neighborhood, has its porch light on a timer. There's something I want to leave you with, and it isn't a fact. When we look up, we tend to imagine the universe is either teeming with company or completely alone, crowded or empty. But there's a third possibility, and it might be the truest one. The universe could be neither. It could be a place where life happens and then doesn't, where worlds hit their billion good years and then go quiet, where the porch lights stay on long after everyone has gone home. That doesn't make us less rare. If anything, it makes us more so, not because nothing else ever made it, but because something else once did, somewhere, and stopped, and we are still here. For now, Earth's window is open. The window won't be open forever, but it's open tonight. The oceans are still liquid. The air is still breathable. The magnetic field is still up. The geological clock that keeps the carbon dioxide cycle balanced is still running. The species are still adapting. The seasons are still turning. The thing that planets only get to do for a sliver of their lives, the thing called supporting life, is something this planet is currently doing. You are an example of that. You're reading this or listening to this or drifting towards sleep with this in background because Earth is, at this moment, allowing it, somewhere, on a world we haven't found yet. The same conditions may be true tonight, and someone on that world might be looking back at a sky that includes our sun, wondering the same thing you're wondering. Maybe they're putting it into words, in a language that has nothing in common with ours. Maybe they're not using words at all. Maybe they just have an internal sense, in whatever counts for them as awareness, that the night is large and that they are a small part of it, and that something might be looking back. Or maybe they're not. Maybe their lights went out a long time ago, and we haven't noticed yet. Maybe the light we'd need to see them, to confirm they were ever there, is still on its way to us, taking centuries or millennia to make the trip. Maybe, by the time we get the message, the senders won't exist anymore, and we'll have to figure out, from a message alone, what they meant. Maybe nobody is out there at all, and the universe is empty in the way the loudest version of the loneliness argument claims it is. Maybe Earth really is the only place where the chemistry came together. Maybe we are, in a literal sense, the only living thing in this galaxy, or in any galaxy we'll ever see. That last one is a possibility you can also sit with. It doesn't have to be the most likely answer. It just has to be allowed. The fact that we don't know is the actual situation. Not knowing is not a problem to solve tonight. It's a place to sit for now until more information comes in. Some of it will, some of it won't. The universe is patient. The universe is also old enough that it can afford to be patient. We have less time than it does, but we have enough time for tonight. Either way, the porch light is still on here. The sky is still up there. The numbers still work. The water is still liquid. The lungs still breathe. The rocks under your feet are still old enough to remember things you can't imagine, and stable enough to keep doing the slow work of holding the planet together for another billion years. Give or take. Mars's porch light is still on, in the technical sense that the sun still shines on Mars, even though the house is empty. Venus's porch light is still on too, in its own way, behind sulfuric clouds, on a planet that is glowing hot under a sky that is heavy and dim. TRAPPIST. One is still flaring 6 times a day. The library is still standing. with its lights mostly out and its shelves still full. The mailbox is still receiving. And here, tonight, you're inside a moment that most planets never get to have at all. You don't have to do anything with that. You don't have to feel awe or sadness or anything in particular. You can just notice it. The window is open. You're in the room. The light is warm. The night will end the way nights end. The morning, if there's a morning where you are, will come. The seasons will keep turning. The Earth will keep doing what it's been doing for 4 billion years, for as long as it can. The lights are on here. For now, if I had to give you one thing to take with you from all of this, it wouldn't be a fact. The facts are out there. You can look them up. The number of confirmed exoplanets will change between when this is recorded and when you hear it, because new ones get added every month. The exact age of Mars's magnetic field will get refined by the next paper. The Venus models will get adjusted. The estimate of how long Earth has left will move by a few 100 million years in one direction or the other, depending on which model team has the latest run. The numbers are not the point. The point is the shape of the picture they make when you put them all together. The shape is something like this. The universe makes worlds. The worlds get a window. Some of the worlds use the window. Most of the worlds don't, as far as we can tell. But our ability to tell is limited. The windows close. The worlds keep existing in some form after the windows close, but they go quiet. The galaxy fills up over time with quiet worlds whose windows have already shut. The few worlds whose windows are open right now are scattered through the dark, separated from each other by distances and times that make finding each other extremely hard. Most of them will probably never find each other. We are one of those worlds, right now, tonight, for a window that is wider than any individual life can use, but narrower than the planet's own history. We're inside the gift. The gift is the only one we ever got. The gift is enough. Sleep well.